Hello, y'all. Darrell Berry Jr. back from earlier. So I found out what the issue was with the two problems I had questions about. So the idea would be to continue with that. So everything should be in place. And if you recall, those who were here earlier, the question I had was about this part here, the Maxwell relation. So I talked with my professor and I got some clarification on that. So let me see if I could elucidate and uh, build upon what we finished earlier. So those who are uh, joining initially on this one, notice this is part two, and there's a part one of the chapter 5 level problems that I just finished doing just about an hour ago. So this is a continuation of that. So the idea is that in just regular mathematics, you can have, for instance, let's say we have an equation f of xy equals x squared y cubed. So partial f partial x equals 2x y cubed, and partial squared f partial y equals 6xy squared. Partial f partial y equals 3x squared y squared, and partial squared f partial uh, squared y partial x. I think I'm mixing these up. I think no, sorry. The one that you do first should go on the right side if I'm remembering properly. So the second derivative with partial x now should still be 6xy squared. So we can see that partial f partial x partial f partial y equals partial f partial y partial f partial x. So we can see that the partial derivative, in whichever order we do it in, is the same. And I guess technically I should remove this f here. And this is the law of mixed partial derivatives if the partial derivatives are agreeable. And we can see that just x squared and y cubed, there's normal functions, doesn't really cause an issue with anything. All right. So how this applies to the equation we have right now is we have one equation that's the partial of g with respect to t, and one is the partial of g with respect to t. So I'll make these partials. So what we're going to do is, and this is equivalent to a Maxwell relation. Law of partial derivatives is this, and this is equivalent to a Maxwell relation when applied to thermodynamics stuff. So all we have to do now to get the Maxwell relation, which is the law of partial derivatives applied to thermodynamic stuff, is do the same thing. So it should be that partial with respect to t, partial g, partial p should equal partial with respect to p, partial g, partial p. So all I'm doing is just taking these two and mixing them up in the same way. So in this case, partial x is like partial t, and partial y is like partial p. And we're saying in the same way that those are equal, when we're dealing with math, it's the same way these two are equal, dealing with thermodynamic properties. And I have the partial derivative with respect to t of g, which is negative s. So we can say negative partial s with respect to t equals partial v with respect to p. And we know that this is the pressure is constant for the entropy one. And we know that the temperature is constant for the pressure one. And I believe this makes this a Maxwell relation. All right. That seems a if I mix something up. I did. So dg of dt is s. Maybe I should swap these to make them all right. Now we have the partial p, and we have the partial t, and we have the g. And we know partial p, partial g, partial p is v, and partial g, partial t is negative s. Did I mix it up still? All right. That's what I'm doing. This is p, and this is t. But I have the principle down, I have to work on my execution a bit. But that's the idea. This This becomes orange, and I guess this becomes technically brown. We have still the partial P on the left. We have the partial T on the right. dg dt negative S on the left. dg dp V on the right. I wonder why is entropy was when the pressure is constant. Now it becomes when the temperature is constant. I guess whenever you um, do this, you end up with these same, at least the alternating derivatives that we're taking, and we just swap those out. So how do we draw something that illustrates this? How do we check the textbook? So they're talking about mixed partial derivatives. They're talking about in general. And I noticed those who've been watching, I have to put things in math form to make it make sense for me a lot. So you notice they wrote in the textbook here, they wrote the just, I guess just random thermodynamic variables U, S, and V, and I end up writing just X and Y as a function of F. I guess the equivalent over here, we can go to our trusty uh, piston. We can say change in V. We can put a flame here. For change in T. And if the pressure stays the same, change in P equals 0. We can say this equals, we have a box with so many particles, change in N equals 0, and we the entropy is changing because stuff is leaving out, and the pressure is changing. So perhaps this is what this means. the values that we get for this can be equal depending on how volume changes and temperature changes versus how entropy changes and pressure changes. All right. And we did 5. And I have one more I want to do. This is probably the one I had well, I guess I can't say the most difficulty with because I didn't score the lowest on, well, I scored tied for the lowest. But the idea is that we have, okay, so Gibbs free energy is a quantity that um, the lower the Gibbs free energy of a substance is, the more likely, or I should say the most stable that substance is in the environment. So if change in G in kilojoules, A is less than change in G B in kilojoules, then this is more stable and this is less stable. And why don't we, and technically we got an idea of what Gibbs is from here. The value is going to be the energy, internal energy of the system, minus the temperature times its entropy, plus its pressure times its volume, which is basically work. And looking at the formula sheet, I may be able to equate these to some things. Okay, so Helmholtz equals, no, enthalpy equals U plus PV. And this is Helmholtz equals U minus TS. So this is enthalpy, and this is Helmholtz. So if we have elements, let's say ironite, and has a change in G of negative 2443.88, and andesite, the change in G of negative 2442.66, and sillimanite, which a change in G of negative 244.0.99. We know that if it's more stable. And let me get a drink of water. She'll be right back. So that's the most stable. Given all three of these is in the same environment. So let's say this is for 1 mole at equals N to 98 K equals T, and 1 bar equals P. So given this condition, we know that kyanite is the most stable. And calculate the temperature at which one of the other phases should become stable at the same pressure. So we say that change in S equals 0 and change in V equals 0. E, another stable. So the idea, I asked my professor about this one as well while I was in office hours. I have earlier we learned that S equals negative GT over GT, GT, dg over dg over dt. So negative S equals partial G over partial T, given constant pressure and number of particles. We want the time when the GT of these things are the same. So if we have GT and lastly we have G and we have that we want the temperature T. But at some point, these things are going to cross, and cross point is T. That other element is more stable. Right. So we want to find where G is the same at a certain T, and we have an equation for G at a certain T, with S being the same, with S being constant. So we can say negative S partial T equals partial G. So we can say G as a function of temperature is whatever the G initially was minus S change in T. Which is to say G at T naught minus S change in T. So where G, K, T equals G, A, T, or G, S, T equals G, K, T. So we need these. So the mistake I made in the problem is to use the pressure one. So we can say, let me see how I'm progressing. We can say I'll do the first one. You can say G, K, T naught minus S, K, change in T equals G, A, T naught minus S, A, change in T. So I need to solve for change in T, it looks like. So we can say S, A, change in T minus S, A, change in T equals G, A, T naught minus G, A, T naught. We can say change in T, S, oh, change in T, S, uh, changing TS A minus SR equals GA T naught minus GA T naught. So we can say change in T equals GA T naught minus GK T naught over SA minus SK. So this equals GA T naught. I wrote it down as, just copy these. I'm checking to make sure I copy the right values. GA T naught. Minusing that, so that's plus divided by, so SA from the sheet. Oh, and I gotta remember that this is kilojoules. And this is divided by SA, which is 93.22 minus 83.81. So I'll break out the calculator. Got my paper. We have negative 2442.66 plus 2443.88 times 10 to the 3. That equals 1220. Joules. Right. So I multiply that times 10 to the 3 to get joules out of it. And the bottom is 93.22 minus 83.81. So this is 9.41 joules over K. So this equals 129.65. It's a change in temperature. So 298 plus 129.65 equals 427.65. And that could be the right answer. Thanks for who's watching. If you have any questions or comments, drop a line. I realized I didn't put the writing on until later in the stream, so that's bad. I might cut it for the first few problems or the first problem. But I don't know. I'll see how it goes. So I think that's that. I think that's the last one that I needed to do. I'm gonna take a look and see here. So to recap, so y'all can see the ones that were missed earlier. I did heat engine concept. This is from the last video, part one of this. I did phase transition concept. Um, and I did deriving thermodynamic identity and the Maxwell relation. The thermodynamic identity is just taking the derivative of the equation of the function. So the thermodynamic identity for G is just basically dg here. And the Maxwell relation, this is what I was covering earlier for those who didn't see, is the law of partial derivatives applied to thermodynamic properties. Then I did just now finding the temperature at which something is more stable. And it's going to be more stable. So if something is, I need to ask why. Why is it a higher temperature? Why does the temperature go up and not down? Looks like there is actually one more I can do. I'll go ahead and do that one. It's pretty short. So thanks for watching. Be sure to drop a line in the live chat or in the comments later. Subscribe if you haven't. Let me know if you have any questions. I'll do one more problem. So we have a mole of particle n equals 1 mole uh, ideal gas. And actually, while I'm looking at this, oh, that's good. Actually, hold up. So I wanted to G1 equals G2 T of crossing. All right. 1 mole of ideal gas. Uh, T equals 300 K. P equals 10 to the 5 pascals, which is 10 to the 5 newtons per meter squared. All degrees of freedom are active. Change in T equals 3K. Change in P equals 0. And what is the change in entropy? So with this problem here, we could just use a simple formula. We can say change in S equals Ti Tf. C, which is the heat capacitance as it relates, divided by T dt. And here Ci equals Cp since the pressure stays the same. And Cp equals Cv plus R. And Cv equals Nrf over 2. That's just the degrees of freedom. And since this is a monatomic gas, F equals 3, 4. Hey, what's going on, Catherine? Hi there. I hope you're having a lovely day. I can't chat just now. I'm about to wash up and listen in. Sounds good, Catherine. So hopefully you enjoyed this last problem. Thank you for dropping a quick line. So F is 3 for monatomic gas. And let me check that, by the way, on my formula sheet. Monatomic. Right. Oh, this must be an old formula sheet. There it is. I see it. Yeah. For monatomic gas, F is 3. So that means Cp equals 1 R 3 over 2 plus R equals R 3 over 2 plus 2 over 2. So that equals 5 over 2R. Then I could just plug this in. Should have enough space here. Change in S equals integral 300 to 303, 5 over 2R dt over t. So that becomes 5 over 2R ln, and these are Kelvin. 3 over 303 divided by 300. And the others watching, let me know if you have any questions. Is that seems right. Let me check my previous work. Yeah. So well, I messed up on this problem with my definition of Cp. Cv is Nrf over 2. Cp is Cv plus R. So the heat capacitance when the volume changes is Nrf over 2. The heat capacitance when the pressure, doesn't change. When the volume doesn't change, when the pressure doesn't change, is the heat capacitance when the volume doesn't change plus R. and everything looks good. So this becomes, I'll break out the calculator, and R equals from the formula sheet, 8.31 joules per moles K. And we know it was 1 mole. Now we just have joules over K. So this should equal 5 divided by 2 times 8.31 times ln 303 divided by 300. So that equals 0.207. And if we did the integral from 300 to 297, change in S equals magnitude of change in S equals 0.209. So change in S is about 0.208, and that should be the right answer. I have to remember what TP is, which I've already added to my new formula sheet. So awesome. Hopefully y'all enjoyed. Apologies for the earlier screen not showing, but did a real little review so y'all can see what I had. I might just cut the first part out, start with the part where it was showing, and I'll be back. Well, studying for the final, so I find myself studying a lot. So I'll probably be back again tomorrow at some point. I won't guarantee. I'll see what's going on, but I'll definitely be back Friday on my other channel for the overview of putting a subatomic particle within a magnetic field. We'll look at Zeeman effect, fine uh, uh, tuning effects. I'll be meeting my tutoring student on Saturday to discuss fluid mechanics, fluid dynamics. So I may talk about that at some point. I'm not sure. I may have an impromptu on that, but most likely not. I'll just refresh myself on that to make sure I cover it with him well, and continue with my final exam studies, which are coming up in a week and a half and a week and 3/4. So preparing for that. Hopefully it goes well. Wish me luck. Uh, Thanks everybody who watched. Thanks Catherine for taking a moment, even though you're busy, to drop a quick line. I appreciate it. And I'll look for you all tomorrow, most likely. Definitely by Saturday. And have a good one.